Saturn's rings are the most famous structure in our solar system. They stretch roughly 270,000 kilometers across, wide enough to fit 21 Earths side by side. For centuries, we assumed nothing could rival them. We were wrong. Roughly 450 light-years away, astronomers detected a ring system so enormous it makes Saturn look like a toy. This structure spans approximately 180 million kilometers in diameter. That is wider than the distance between Earth and the Sun. It contains at least 37 individual rings, gaps where entire moons may be forming, and enough material to build a planet the mass of Earth. This is not a slightly bigger version of Saturn. This is something that should not exist. If you enjoy journeys through discoveries that completely reshape how we see the universe, consider hitting that like button and subscribing. I genuinely appreciate every one of you that helps this channel keep making content like this. Now, get yourself comfortable. Let's begin. In 1610, Galileo Galilei pointed a crude telescope at Saturn and saw something he could not explain. The planet appeared to have ears. Two strange bumps flanked the bright disk, bulging outward like handles on a ceramic cup. His instrument was too weak to resolve what he was actually seeing. He sketched the planet as a trio of overlapping circles and moved on, puzzled but unable to investigate further. 2 years later, when he looked again, the ears had vanished entirely. Saturn appeared perfectly round. Galileo was so confused that he reportedly wondered whether the planet had devoured its own children, echoing the myth of the Roman god for which it was named. He never solved the mystery. He died in 1642 without knowing what those strange protrusions actually were. It took another 13 years for someone to figure it out. In 1655, the Dutch astronomer Christian Huygens built a more powerful telescope and turned it towards Saturn. What he saw changed astronomy permanently. The planet was not flanked by two smaller bodies. It was surrounded by a thin, flat disk that did not touch the planet at any point, tilted at an angle to our line of sight. Huygens had discovered Saturn's rings. He published his finding cautiously, encoding the announcement as an anagram before eventually revealing the full description. Saturn, he wrote, is girdled by a thin, flat ring, nowhere touching, inclined to the ecliptic. It was elegant and strange and unlike anything anyone had ever seen around a planet. 20 years later, Giovanni Cassini discovered something even stranger. The ring was not a single unbroken structure. It was divided by a dark gap, a separation nearly 5,000 kilometers wide that split the bright disk into two concentric bands. That gap now bears his name, the Cassini division, and it was the first indication that Saturn's rings were not a simple sheet of material, but a complex system with internal architecture shaped by gravitational forces. Over the following centuries, telescopes improved and Saturn's rings revealed layer after layer of hidden detail. What appeared as a smooth disk from a distance turned out to be thousands of individual ringlets, each one a separate band of orbiting particles. The main rings, labelled C, B, and A from innermost to outermost, became the most studied features in the solar system. Beyond them, astronomers discovered additional rings labelled D, F, G, and E, each with different properties and each telling a different story about how material behaves under Saturn's gravitational influence. The dimensions of this system are striking in their own right. Saturn's main rings, from the inner edge of the C ring to the outer edge of the A ring, span approximately 270,000 kilometers. That is roughly 21 times the diameter of Earth. If you could lay Earth side by side across the ring system like coins on a table, you would need more than 20 of them to bridge the gap. The outermost diffuse E ring extends even farther, reaching approximately 480,000 kilometers from Saturn's center. Including the faint Phoebe ring discovered in 2009, the full extent of Saturn's ring influence stretches millions of kilometers into surrounding space. Yet for all their width, Saturn's rings are astonishingly thin. The main rings average roughly 10 meters in vertical thickness. 10 meters. That is shorter than a 4-story building. If you scaled Saturn's rings down to the diameter of a football field, their thickness would be thinner than a razor blade. This extreme thinness is one of the most remarkable features of any structure in the solar system. The rings are vast in 2 dimensions and essentially flat in the third, a cosmic sheet so proportionally thin that nothing in human engineering comes close to replicating the ratio. The rings are composed of billions of individual particles, ranging in size from tiny grains of dust to boulders the size of houses. A small number of chunks are as large as mountains. Nearly all of this material is water ice, sometimes coated with traces of rocky dust and organic compounds. The particles orbit Saturn independently, each one a tiny moon following its own path around the planet. Inner particles orbit faster than outer particles, following the same laws of orbital mechanics that govern planets circling the Sun. The entire ring system is not a solid object. It is a vast swarm of icy fragments, each one reflecting sunlight and contributing to the bright, flat disk that has captivated every civilization that has ever looked up at Saturn through a telescope. For most of recorded astronomical history, scientists believe Saturn's rings were ancient, perhaps as old as the solar system itself, roughly 4.5 billion years. That assumption persisted until NASA's Cassini spacecraft arrived at Saturn in 2004 and spent 13 years studying the planet and its rings in extraordinary detail. Cassini's measurements told a different story. The rings appeared surprisingly clean. If they had been orbiting for billions of years, they should have accumulated far more dust and debris from micrometeoroids bombarding them over cosmic time. The relative purity of the ice suggested the rings were much younger, perhaps only 100 to 200 million years old. Some estimates pushed the age even lower. This was a dramatic shift. If Saturn's rings formed only a few 100 million years ago, they appeared while dinosaurs still walked the Earth. They are not permanent fixtures of the solar system. They are temporary, and they are eroding. Cassini measured material falling from the rings into Saturn's atmosphere at a rate that would drain the entire ring system in roughly 300 million years. Saturn's rings, the most iconic planetary feature in the solar system, are a passing phase. They were not always there. They will not always be there. We happen to exist during the relatively brief window in which they are visible. This realization raised a question that had never been urgent before. If Saturn's rings are temporary, could similar ring systems exist elsewhere? Could they form around other planets, under different conditions, at different scales? And if so, how large could a ring system actually get? The answer within our own solar system appeared to be clear. Ring systems are common but modest. Jupiter has a faint ring system discovered by the Voyager 1 spacecraft in 1979. These rings are thin, dark, and composed primarily of tiny dust particles knocked off Jupiter's small inner moons by micrometeoroid impacts. They are essentially invisible without specialized equipment. Uranus has a system of narrow, dark rings, discovered in 1977 during a stellar occultation, when the planet passed in front of a distant star and the rings briefly blocked the starlight before and after the planet itself did. Neptune has faint rings as well, including arcs of concentrated material that clump together in ways scientists still do not fully understand. All 4 giant planets in our solar system possess ring systems, but none of them come close to rivaling Saturn. Saturn's rings appeared to represent a kind of natural ceiling. They were the widest, the brightest, the most structurally complex ring system known. Everything else was a pale imitation. For decades, no observation suggested that anything in the universe exceeded them. Textbooks treated Saturn as the ultimate example of what a ring system could be. And that assumption held firm until a small group of astronomers started paying attention to a young, unremarkable star, roughly 450 light-years away in the constellation Centaurus. The star's full catalogue designation is a mouthful: 1 SWASP, J140747.93, -39454, 2.6. Astronomers shorten it to J1407, or by its variable star name, V1400 Centauri. It is a pre-main sequence star, meaning it is still in the early stages of its stellar life. Its age is estimated at roughly 16 million years. In cosmic terms, this star is a newborn. Our Sun is approximately 4.5 billion years old. V1400 Centauri has existed for less than 0.5% of that time. It is roughly the same mass as the Sun, but it rotates much faster, completing one full spin every 3.2 days compared to the Sun's 25-day rotation period. That rapid spin is typical of young stars that have not yet been slowed down by magnetic braking over billions of years. The star sits within the Scorpius-Centaurus Association, a loose grouping of young co-moving stars that formed from the same molecular cloud. This association is the nearest such grouping of young stars to our solar system, with member stars scattered at distances between roughly 380 and 470 light-years from Earth. V1400 Centauri belongs to the Upper Centaurus Lupus subgroup, which has an estimated age range of 14 to 18 million years. None of this would be particularly noteworthy on its own. Young sun-like stars are common in the galaxy. This one attracted no special attention for years. The data that changed everything was collected not by a human observer squinting through a telescope eyepiece, but by an automated survey called SuperWASP, the Super Wide Angle Search for Planets. SuperWASP is a ground-based transit survey that monitors the brightness of millions of stars simultaneously, watching for the tiny periodic dips in light that occur when an orbiting planet passes in front of its host star from our perspective. A typical gas giant like Jupiter causes a brightness dip of about 1% when it transits a sun-like star. These dips are small and fleeting, lasting a few hours at most, and finding them requires monitoring vast numbers of stars continuously over long periods. In 2007, SuperWASP's cameras recorded the light from V1400 Centauri along with millions of other stars. The data was archived automatically, stored in a digital database, and left largely unexamined for years. Nobody was looking at this particular star for any particular reason. It was just one faint point of light among countless others, dutifully monitored by robotic telescopes and forgotten. 3 years passed. In late 2010, Mark Pacaut, a graduate student working under the supervision of astronomer Eric Mamajek at the University of Rochester, was browsing the SuperWASP public light curve database. He was not looking for rings. He was not looking for anything unusual around V1400 Centauri specifically. He and Mamajek were investigating brightness variability among candidate low-mass stars in the Scorpius-Centaurus Association, a routine survey project aimed at understanding the properties of young stellar populations. But when Pacaut pulled up the light curve for V1400 Centauri, he saw something that stopped him cold. The star's brightness had not dipped by 1% for a few hours, which is what a transiting planet would produce. The star had dimmed dramatically, erratically, and for an extraordinarily long time. The dimming event began in April of 2007 and continued for approximately 56 days. During that period, the star's brightness fluctuated wildly. On some nights, it dropped by a few percent. On others, it plunged by 30, 40, 50%. At the deepest point of the event, the star's brightness fell by more than 95%. Nearly all of its light was being blocked by something passing in front of it. No known planet could do this. Even the largest gas giant in a tight orbit around a sun-like star blocks only a small fraction of the star's light during transit. A 95% drop would require an object far larger than any planet, something with a cross-sectional area enormous enough to cover nearly the entire stellar disk as seen from Earth. And the event lasted not hours but weeks. Whatever was crossing in front of V1400 Centauri was moving slowly. It was vast, and it had complex internal structure. The brightness variations were not smooth. They changed on timescales of tens of minutes, flickering up and down in rapid, irregular patterns that suggested the blocking material was not a uniform disk, but a collection of concentric regions with different densities and opacities. Pacaut and Mamajek recognized the significance immediately. they brought in additional collaborators and began a detailed analysis of the light curve. The first formal announcement came in January of 2012 at the 219th meeting of the American Astronomical Society. The peer-reviewed paper followed in March of that year, published in the Astronomical Journal. In it, the team proposed that the extraordinary dimming of V1400 Centauri was caused by a massive ring system, or circumplanetary disk, surrounding an unseen substellar companion orbiting the star. They called the companion J1407b. The initial model was conservative. Based on nightly average brightness measurements, the team proposed at least 4 large rings around the companion, but the data contained far more detail than nightly averages could capture. The raw super-WASP measurements showed brightness variations on timescales as short as 10 minutes, meaning the ring system had fine structure that the initial model had smoothed over. A more thorough analysis was needed to extract the full complexity of what the light curve was revealing. That deeper analysis came in 2015, led by Matthew Kenworthy of Leiden Observatory in the Netherlands, working with Mamajek. Their paper, published in the Astrophysical Journal, presented a detailed model of the ring system based on the rapid brightness variations in the raw data. The results were extraordinary. The best fit model required not 4 rings but 37. 37 distinct concentric rings, each with its own width and opacity, separated by gaps of varying sizes. The outermost ring extended to a radius of approximately 0.6 astronomical units from the central object. 1 astronomical unit is the average distance between Earth and the Sun, roughly 150 million kilometers. That meant the ring system had a radius of approximately 90 million kilometers and a total diameter of approximately 180 million kilometers. To understand what this number means, consider Saturn's main rings one more time. From inner edge to outer edge, they span roughly 270,000 kilometers. The ring system around J1407b spans approximately 180 million kilometers. That makes it roughly 200 times larger than Saturn's rings. Not 200% larger, 200 times larger. If Saturn's entire ring system were a dinner plate sitting on your kitchen table, the J1407b ring system would be a disk approximately 50 meters across, stretching from the center of your house to well past the end of your street. Kenworthy offered a simple way to grasp the difference. If these rings replace Saturns in our solar system, he noted, they would be easily visible from Earth without any telescope at all, not as a faint astronomical curiosity, as a dominant feature of the night sky, impossible to ignore, impossible to miss. That single observation captures the gulf between what we thought ring systems could be and what this one actually is. The model also revealed something beyond sheer scale. The ring system contained gaps, clear regions where the opacity dropped sharply, separating adjacent rings with distinct boundaries. One gap in particular stood out, located at a radius of approximately 0.4 astronomical units. This gap measured roughly 4 million kilometers wide. In Saturn's ring system, gaps like this are carved and maintained by orbiting moons whose gravity clears particles from their path. The same logic applied here. The prominent gap in J1407b's ring system suggested that a satellite was orbiting within it, sweeping the region clean of material. Kenworthy and Mamajek estimated that such a satellite would need a mass less than 0.8 Earth masses to produce the observed gap width. Assuming the gap diameter equals the diameter of the satellite's Hill sphere, the region in which the satellite's gravity dominates over that of the central object. This was not just a ring system, it was a ring system with moons forming inside it, or at least that was the most natural interpretation of the data. If correct, it meant that the J1407b system was not a static collection of debris, it was a dynamic structure caught in the act of building new worlds. The gaps represented construction zones where gravitational forces were assembling material into coherent bodies, pulling dust and ice together into objects that might one day become moons comparable to the large satellites orbiting Jupiter and Saturn. The total mass of the ring system, estimated from the amount of starlight it blocked, was approximately 100 lunar masses. That is roughly 1.23 Earth masses worth of material, distributed across a disk 180 million kilometers wide. For comparison, Saturn's entire ring system contains far less mass than even Saturn's small moon Mimas, which has a diameter of only about 400 kilometers. The mass of Saturn's rings is estimated at roughly 40% of Mimas, or about 1.5 times 10 to the 19th kilograms. The J1407b disk contains roughly the mass of our entire planet, compressed into a flat structure spanning a region larger than Earth's orbit around the Sun. Mamajek described the implications in characteristically vivid terms. If you could grind up the 4 large Galilean moons of Jupiter, Io, Europa, Ganymede, and Callisto, into dust and ice and spread that material over their orbits in a ring around Jupiter, you would get something similar to what was observed around J1407b, a disk so dense with material that it blocks nearly all the light from a background star, a structure containing enough mass to build an entire system of large moons, a ring system that is not merely decorative, like Saturn's gossamer bands of ice, but constructive, actively assembling the architecture of a new planetary system. The initial announcement generated considerable excitement and considerable skepticism. A ring system 200 times larger than Saturn's, discovered through a single unrepeated eclipse event around a companion whose mass, orbit, and fundamental nature remained entirely uncertain. The light curve fit was compelling, but it was a model, a reconstruction, not a direct image. Nobody had seen the rings, nobody had seen the companion. All that was confirmed was that something had blocked 95% of V1400 Centauri's light for nearly 2 months in 2007, and that a ring system around a substellar object was the best available explanation. The questions came fast. How massive was the companion? Was it a giant planet like Jupiter, or something heavier, a brown dwarf straddling the boundary between planet and failed star? What kind of orbit did it follow? If it orbited the star on a wide elliptical path, how could such an enormous ring system survive the gravitational stresses of each close approach to the star? Why had no second eclipse been detected in the years since 2007? Was the companion still orbiting the star at all, or had it been a chance alignment with a free-floating object drifting through interstellar space? None of these questions had clear answers. What was clear was that the scale of this structure broke every assumption astronomers had carried about ring systems. Saturn was no longer the ceiling. Saturn was not even close. Something existed in the constellation Centaurus that made the most iconic rings in our solar system look like a thin band of frost around a pebble. The data said so. The models said so. The light curve, recorded by robotic cameras and filed away in a database for 3 years before anyone noticed, said so. And the story of what that structure actually was, how it formed, whether it could survive, and what it meant for our understanding of how moons and planets are built, was only beginning to unfold. Numbers have a breaking point. Push them far enough and they stop functioning as information. They become decoration, symbols on a page that the brain skims over without processing. 180 million kilometers is one of those numbers. You can hear it, you can repeat it, but your mind does not hold it. It slides off the surface of your comprehension like water off glass. And that is exactly the problem with the ring system around J1407b. Its dimensions exist in a range where human intuition fails completely, where the numbers are so large that stating them plainly conveys almost nothing. So the only way to understand what this structure actually is, the only way to feel its scale rather than merely acknowledge it, is to drag it out of the abstract and anchor it to things you already know. Start with the distance between Earth and the Sun. That distance, 1 astronomical unit, is approximately 150 million kilometers. It is the baseline measurement for our entire solar system, the yardstick astronomers use to describe the spacing of planetary orbits. Light covers that distance in approximately 8 minutes and 20 seconds. A commercial airplane flying non-stop at cruising speed would take roughly 17 years to make the journey. The entire ring system of J1407b, at 180 million kilometers in diameter, is wider than this distance. If you place the central object at the Sun's position, the ring system's outer edge would extend past the orbit of Earth and reach approximately 20% of the way toward Mars. The entire habitable zone of our solar system, the narrow band where liquid water can exist on a rocky planet's surface, would sit inside this ring system. Earth itself would be embedded within the rings, orbiting through a dense field of dust and ice particles like a marble rolling through a fog bank. Now consider what that means in terms of light travel time. Light is the fastest thing in the universe. It crosses the vacuum of space at approximately 300,000 kilometers per second. At that speed, light travels from one edge of Saturn's main rings to the other in less than 1 second. Roughly 9/10 of a second, to be more precise. The rings are wide by human standards, but trivial by the standards of light. The J1407b ring system is a different proposition entirely. Light requires approximately 10 minutes to travel from one edge of this disk to the other, 10 minutes at the fastest speed the universe permits. That is longer than light takes to travel from the Sun to Earth. If you stood on one edge of this ring system and fired a laser pointer toward the opposite side, you would wait longer for the beam to arrive than you wait for sunlight to reach your face each morning. For a spacecraft, the comparison becomes almost absurd. NASA's Voyager 1, the fastest human-made object to leave the solar system, travels at roughly 17 kilometers per second relative to the Sun. At that speed, crossing Saturn's main rings would take approximately 4 hours and 25 minutes, a manageable journey. Crossing the J1407b ring system at the same speed would take roughly 122 days. More than 4 months of continuous travel at 17 kilometers per second just to get from one side of a ring system to the other. And that is not crossing an interstellar void or traveling between planets. That is traversing a structure that surrounds a single object, a structure made of dust and ice and the raw materials of forming moons. Bring the comparison closer to home. The Moon orbits Earth at an average distance of approximately 384,000 kilometers. The entire diameter of the Moon's orbit, from one side to the other, is roughly 770,000 kilometers. The J1407b ring system is approximately 234 times wider than the Moon's orbit. You could line up more than 230 copies of the Moon's complete orbital path, side by side, and still not span the full extent of this disk. Every time you have looked up at the Moon and marveled at how far away it seems, remember that the distance between you and the Moon is a tiny fractional sliver of the space this ring system occupies, or consider it from the perspective of the planets in our solar system. Mercury, the innermost planet, orbits the Sun at an average distance of approximately 58 million kilometers, giving it an orbital diameter of roughly 116 million kilometers. The J1407b ring system is wider than Mercury's entire orbit around the Sun. Venus orbits at approximately 108 million kilometers from the Sun, with an orbital diameter of roughly 216 million kilometers. The ring system is slightly narrower than the orbit of Venus, but comparable in scale. In other words, this single ring system around a single substellar object occupies a region of space comparable to the inner solar system. Not a planet, not a star, a ring system. A disk of debris and dust takes up as much room as the orbital paths that Mercury and Venus trace around our Sun over the course of an entire year. These comparisons are not exaggerations. They are the direct mathematical consequences of a disk with a radius of 0.6 astronomical units. And they are necessary because without them, the number 180 million kilometers sits on the page doing nothing. With them, you can begin to feel the wrongness of this structure. Ring systems are not supposed to be this large. Nothing about our experience with Saturn, Jupiter, Uranus, or Neptune prepares us for a disk that spans an entire planetary orbit. The ring systems we know are compact features hugging close to their parent planet, constrained by gravitational physics to a relatively narrow band around the equator. They are delicate, they are thin, they are, in the grand scheme of things, small. The J1407b ring system violates every intuition these familiar examples build. But all of these comparisons describe the disk from the outside as a measurement, a shape drawn on a map. They do not tell you what it would be like to exist inside it, and that perspective matters because a structure this large is not just something you observe, it is something you inhabit. If a world orbited within this disk, its sky would be defined by the disk's presence. So consider, for a moment, what the interior of this system would actually look like. Start at the center. Imagine standing on the surface of J1407b itself, if it has a surface, or floating in its upper atmosphere, if it is a gas giant or brown dwarf. Look outward. The innermost ring begins approximately 31 million kilometers away. That is roughly 80 times the distance between Earth and the Moon. You would not see a wall of material. You would not see a visible ring arching overhead the way Saturn's rings appear from Saturn's cloud tops. The nearest ring material would be so distant that individual particles would be invisible. What you might perceive, depending on the density of material and the ambient light, is a faint diffuse glow stretched across the plane of the disk, a band of scattered light smeared across the sky like a dim, flat version of the Milky Way. The rings would not look solid, they would look like haze, a whisper of brightness marking the plane where dust and ice orbit in vast, slow circles. Now, move outward. Travel to the dense inner rings, 31 million kilometers from the center. Here, the particle density is at its highest. Material is packed tightly enough to block nearly all the starlight passing through. But tightly packed in disk terms does not mean crowded in human terms. Even in the densest rings, individual particles are separated by distances far greater than their own sizes. You could travel through the densest ring for thousands of kilometers without colliding with a single grain. The density that blocks starlight so effectively is an optical effect, a consequence of the cumulative obstruction caused by trillions of particles spread across a vast cross-sectional area. Up close, the ring would feel eerily empty. Particles of ice and dust drifting in every direction, each one following its own orbital path, separated by gulfs of vacuum that make the space feel deserted despite the enormous total mass. Continue outward. Pass through the transition zones where opacity fluctuates, where dense rings give way to sparse gaps and sparse rings yield to dense bands again. Each ring occupies a different radial zone. Each gap separates one regime of density from the next. At 60 million kilometers from the center, you cross the Great Gap, 4 million kilometers of nearly empty space. This void is wider than Jupiter. Crossing it at orbital speeds would take weeks. Inside the gap, you might encounter the body responsible for clearing it. A forming moon, a world, perhaps the mass of Mars, sweeping its orbital lane clean of debris. This object would not look like a finished planet. It would be rough, irregular, still accumulating material, perhaps surrounded by its own miniature cloud of captured particles and its own tiny accretion disk. A world under construction, orbiting silently through a void it carved for itself inside a disk it is slowly consuming. Beyond the gap, the outer rings thin and spread. Particle density drops. Light from the distant host star, V1400 Centauri, or from surrounding stars in the Scorpius-Centaurus association, would filter through more easily. The outermost rings, near the disk's edge at 90 million kilometers, are sparse enough that the sky beyond would be visible through a veil of scattered particles. Standing here, near the disk's outer boundary, you would be farther from the central object than Earth is from the Sun. The central body would appear as a bright point of light, not a looming giant. The inner rings would be a distant band of brightness near the central glow, and surrounding everything, the black sky of interstellar space, studded with the young bright stars of the Scorpius-Centaurus Association, entirely indifferent to the enormous structure you are standing inside. The experience of being inside the disk would be defined by one overwhelming quality: emptiness. Despite containing an Earth's mass of material, the disk is so spread out, so thin, so geometrically vast that any given location within it would feel like open space. The density that makes the disk opaque from the outside is invisible from the inside. You would know you were in a ring system only by measuring particle concentrations with instruments, not by looking around with your eyes. The disk is a structure that exists at statistical scales, not human scales. It is real, it is massive, it is consequential, but it is also diffuse beyond anything your senses could directly perceive. A ghost structure, present everywhere, visible nowhere. Part of what makes the violation so jarring is the internal structure as revealed by the light curve. This is not a smooth, featureless cloud of debris spreading uniformly across 180 million kilometers. The 2015 analysis by Kenworthy and Mamajek resolved at least 37 individual rings within the disk. 37 concentric bands, each with its own width, density and opacity, nested inside one another like the grooves on an enormously scaled phonograph record. Some of these rings are relatively transparent, allowing a significant fraction of the background starlight to pass through. Others are nearly opaque, blocking almost all the light from V1400 Centauri as they cross the line of sight. The variations in opacity are what made the reconstruction possible in the first place. If the disk had been a uniform sheet of material with constant density, the light curve during the eclipse would have shown a smooth, gradual dimming as the disk moved in front of the star, followed by a smooth, gradual brightening as it moved away. Instead, the light curve was chaotic. Brightness levels jumped and dropped on timescales of minutes. The star would brighten briefly, then dim again, then brighten, then plunge to near total obscuration, then partially recover, all within the span of a single night. These rapid fluctuations correspond to individual rings and gaps passing across the face of the star. Each ring blocks a different fraction of the light. Each gap lets a different fraction through. The star's flickering brightness during the eclipse encoded the entire radial structure of the ring system, like a barcode being scanned by the star's own light. The innermost ring in the model extends to a radius of approximately 31 million kilometers from the central object. This innermost region is also the most opaque, the densest concentration of material in the entire disk. Moving outward, the ring's thin and separate, interspersed with gaps of varying widths. Some gaps are narrow, barely resolved in the data. One gap is enormous. Located at a radius of approximately 60 million kilometers, this clearing spans roughly 4 million kilometers in width. For comparison, that single gap is more than 10 times the distance between Earth and the Moon. It is wider than the diameter of Jupiter. An entire gap in a ring system, a void within a disk, is larger than the biggest planet in our solar system. The presence of gaps is scientifically important because gaps do not form on their own. In a disk of orbiting particles, material tends to spread out smoothly over time through collisions and gravitational interactions. For a gap to exist and persist, something must be actively clearing it. In Saturn's rings, the best understood gaps are maintained by moons. The Encke gap within Saturn's ring is kept open by the small moon Pan, which orbits within the gap and gravitationally scatters any particles that drift too close. The Cassini division is maintained partly by an orbital resonance with the moon Mimas, which orbits outside the rings. The physics is well established. Where you see a clean gap in a ring system, you should look for a moon. Applying the same logic to J1407b, the prominent gap at 60 million kilometers strongly suggests the presence of an orbiting body, an exomoon, massive enough to clear a 4 million kilometer wide lane through the surrounding debris. Kenworthy and Mamajek estimated that such a body would need a mass less than roughly 80% of Earth's mass. That is not a small rock. That is a world comparable in size to Venus or Mars, orbiting within the disk and actively sweeping its neighborhood clean of particles. A second, narrower gap closer to the central object hints at a second possible exomoon, though the evidence for this one is less definitive. If these exomoons are real, they are not just interesting curiosities. They represent a fundamentally different kind of ring system than anything we have in our solar system. Saturn's rings are made of small particles, mostly water ice, with a combined mass less than that of Saturn's tiny moon Mimas. They are not building anything. They are debris, perhaps the remnants of a shattered moon or a captured comet, slowly eroding over time. The J1407b disk, by contrast, contains roughly an entire Earth's mass of material distributed across its 180 million kilometre span. That is enough raw material to assemble an entire family of large moons. The gaps suggest this assembly process is already underway. Material is being gathered, concentrated, and cleared by forming bodies that are growing more massive with each orbit. This reframing changes what the ring system means. It is not just big, it is productive. It is a factory, an active construction site where the gravitational machinery of moon formation is operating at a scale that dwarfs anything in our solar system's present configuration. Jupiter's 4 Galilean moons, Io, Europa, Ganymede, and Callisto, are believed to have formed from a similar circumplanetary disk billions of years ago. Saturn's large moon Titan likely arose through a comparable process, but those disks dissipated long ago, consumed by the very moons they created. We have never directly observed a circumplanetary disk in the act of building satellites on this scale. J1407b, if the interpretation is correct, offers the first observational window into this process. To appreciate how much material the disk contains, consider what one Earth mass of dust and ice looks like when spread across a disk 180 million kilometers wide. The disk is not thick. Despite spanning 180 million kilometers from edge to edge, it is extraordinarily flat, proportionally even thinner than Saturn's already razor-thin rings. If you scaled the disk down to the width of a city block, its vertical extent would be thinner than a coat of paint on the pavement. The material is spread incredibly thinly over an incredibly vast area, a structure that is essentially two-dimensional at any meaningful scale. Yet there is so much of it in total that the disk blocks nearly all the light from a star as bright as the Sun. The density of this material varies enormously from one ring to another. The innermost rings are densest, packed tightly with particles that block almost everything. The outer rings are sparser, allowing more light to filter through. This gradient is consistent with what physicists expect from a circumplanetary disk, in which material slowly spirals inward toward the central object, under the influence of viscous drag and gravitational torques. Fresh material enters the disk from the surrounding environment, drifts inward, and accumulates near the center, while the outer regions thin out over time unless replenished. The total cross-sectional area of the disk is staggering. When projected against the sky, the disk covers more than 40,000 times the area of Saturn's rings. 40,000 times. That number is worth pausing on. Every photograph you have ever seen of Saturn's rings, every image from Cassini or Hubble or ground-based telescopes showing that graceful, luminous disk encircling the planet, represents a structure that would need to be multiplied by 40,000 to match the area of the J1407b system. The visual comparison stops being meaningful at that ratio. You are no longer comparing two objects of different sizes. You are comparing a postage stamp to a parking lot. Kenworthy offered a vivid way to imagine the visual impact of this system. If the rings of J1407b were placed around Saturn in our own solar system, they would be visible from Earth with the naked eye. Not as a faint point of light requiring a telescope, not as a subtle glow detectable only under perfect conditions. They would appear many times larger than the full moon in Earth's sky, a luminous arc stretching across a substantial fraction of the visible heavens. Even from a distance of roughly 1.2 billion kilometers, the distance between Earth and Saturn at their closest approach, this ring system would dominate the night sky. You would see it without trying. You would see it from your window. Children would point at it and ask what that giant bright stripe in the sky was, and the answer would be the rings around a planet nearly 1 billion miles away. That visual test is perhaps the most effective way to communicate the difference between Saturn's rings and this system. Saturn's rings are invisible to the naked eye from Earth. Even through a small telescope, they appear as a tiny bright extension on either side of the planet's disk. You need magnification, dark skies, and patience to see them well. The J1407b system would need none of those things. It would be the most prominent feature in the night sky after the moon. Visible at dusk, visible at dawn, visible from cities, visible from everywhere. The difference between invisible without a telescope and larger than the moon in the night sky is the difference between these two ring systems. There is another way to grasp the scale, one that approaches the problem from the perspective of time rather than distance. The ring system was detected because it passed in front of V1400 Centauri and blocked the star's light. That transit lasted approximately 56 days, nearly 2 months of continuous dimming, flickering, and obscuration. For comparison, when Jupiter transits a distant star as seen from outside our solar system, the transit lasts approximately 30 hours. Saturn's transit would last roughly 40 hours, depending on geometry. 56 days is not in the same category. It is not even in the same conversation. A transit lasting 56 days means the occulting structure took almost 2 months to drift across the face of a star, and V1400 Centauri is not a particularly large star. It is roughly the same size as our Sun, with a diameter of approximately 1.5 million kilometers. The ring system is so wide that even moving at an estimated transverse velocity of 35 kilometers per second relative to the star, it required 56 days to complete the crossing. 35 kilometers per second is itself an extraordinary speed. It is roughly 126,000 kilometers per hour, fast enough to travel from Earth to the Moon in about 3 hours. At that velocity, the ring system still took 8 weeks to pass in front of the star. This transit duration independently confirms the enormous physical extent of the disk and provides a cross-check on the size derived from modelling the light curve. The transit speed and duration together give a diameter of approximately 1.2 astronomical units, consistent with the 0.6 astronomical unit radius derived from the ring model. The numbers agree. The system is as large as the models say it is, and yet, for all its enormity, the disk is not structurally simple. It is not a featureless smear of particles. It is organized. It has rings. It has gaps. It has regions of high opacity and regions of transparency. It has a measurable tilt, approximately 13 degrees relative to the plane of the companion's motion across our line of sight. This tilt is what gives the light curve its nearly symmetrical profile. The ingress, the period when the disk moves onto the stellar disk, roughly mirrors the egress, the period when it moves off. If the disk were edge-on, the symmetry would be perfect. The 13-degree tilt introduces slight asymmetries that the modelling was able to detect and constrain. The disk's organisation raises a critical question that cuts to the heart of what this system actually is. Is this a ring system in the way we understand Saturn's rings? A collection of debris particles orbiting in stable equilibrium around a central body? Or is it something else, something more dynamic, more transient, more structurally significant? Saturn's rings are, in essence, rubble. They are the remains of something that was destroyed, whether a moon torn apart by tidal forces, a comet shredded by Saturn's gravity, or some combination of disrupted objects. They are not building anything. They are the aftermath of destruction, slowly spreading, slowly eroding, slowly being pulled into Saturn's atmosphere. They are beautiful. They are scientifically fascinating. But they are debris. The J1407b disk appears to be something fundamentally different. Its mass, its structure, its gaps, and the evidence for forming satellites all point toward a circumplanetary disk, a structure analogous not to Saturn's present rings, but to the primordial disk from which Saturn's moons originally formed billions of years ago. If this interpretation is correct, we are not looking at the aftermath of destruction. We are looking at the beginning of construction. The disk is the raw material out of which an entire satellite system will be assembled over the coming millions of years. The moons that will eventually orbit J1407b do not yet exist in their final form. They are being built right now, grain by grain, collision by collision, inside a disk so vast it dwarfs everything our solar system currently contains. This distinction between debris ring and constructive disk is not merely academic. It changes the significance of the scale entirely. A debris ring 200 times the size of Saturn's would be surprising but conceptually familiar. Bigger version of the same thing. A constructive circumplanetary disk 200 times the size of Saturn's rings, actively assembling moons on a scale comparable to the inner solar system, is not just bigger, it is categorically different. It belongs to a phase of planetary evolution that we have only theorized about, never witnessed. Every simulation of moon formation around giant planets predicted that disks like this should exist during the early history of planetary systems. But predictions and observations are not the same thing. Predictions are ideas, observations are evidence, and the light curve of V1400 Centauri is evidence that circumplanetary disks on this scale actually form in nature, not just in computer models. The scale of this system also forces a reconsideration of what the word ring means when applied to structures outside our solar system. Saturn's rings are gravitationally confined to a narrow band close to the planet, well within Saturn's Roche limit, the distance inside which tidal forces prevent particles from coalescing into larger bodies. Particles inside the Roche limit are doomed to remain particles. They can never assemble into a moon because Saturn's gravity will tear apart any clump that tries to form. That is why Saturn's rings persist as rings rather than collapsing into moons. The J1407b disk extends far beyond its central object's Roche limit. The Roche limit for this system is estimated at roughly 0.001 astronomical units, approximately 150,000 kilometers from the center. The disk stretches to 90 million kilometers. Almost the entire disk lies outside the Roche limit, in the region where particles can gravitationally coalesce. The gaps prove that they are doing exactly that. This is not a ring system in the Saturnian sense. It is a disk that happens to have ring-like structure, a disk where the physics permits and indeed encourages the formation of large bodies. The rings are not the endpoint, they are the scaffolding, and the scaffolding extends across a region of space so immense that standing at its center, you would have no visual indication that you were inside a structure at all. The nearest ring material might be millions of kilometers away in every direction. A faint haze of particles too sparse to see with the naked eye, but collectively massive enough to block the light of a star. This is the aspect of the J1407b system that no simple size comparison can fully convey. It is not just that the numbers are big, it is that the numbers describe a structure operating under different rules than the ring systems we grew up learning about. Saturn's rings are a museum exhibit, beautiful and preserved and static. This disk is a construction site, chaotic and dynamic and productive, and the construction site is larger than the distance between Earth and the Sun. The next question is unavoidable. How did scientists reconstruct all of this detail from a single 56-day flicker in a star's brightness? And how certain can they actually be about what they found? Nobody has ever seen the rings of J1407b. No telescope has resolved them into an image. No spacecraft has visited them. No camera has captured the glint of starlight off their icy particles. Everything we know about this structure, its diameter, its 37 rings, its gaps, its opacity profile, its tilt, its mass, comes from one thing only: a graph. A plot of brightness versus time, showing how the light from a distant star flickered and faded over 56 days in 2007. That graph is called a light curve, and reading it correctly required one of the most elegant detective techniques in modern astronomy. The method is called transit photometry, and in principle it is remarkably simple. When an object passes between a star and an observer, it blocks some of the star's light. The amount of light blocked depends on the size of the object relative to the size of the star. A planet the size of Jupiter crossing in front of a sun-like star dims the star by roughly 1%. A planet the size of Earth dims it by roughly 0.01%. The shape and duration of the dimming reveal the object's size, speed, and orbital geometry. This is the same technique that NASA's Kepler and TESS missions have used to discover thousands of exoplanets. Point a camera at a star, measure its brightness continuously, wait for something to get in the way. But the transit of J1407b was nothing like a planetary transit. When a planet crosses in front of a star, the light curve shows a clean, predictable pattern. Brightness drops smoothly as the planet moves onto the stellar disk, holds roughly steady while the planet is fully in front of the star, and rises smoothly again as the planet moves off. The entire event lasts hours, produces a flat bottom dip in the light curve, and repeats at regular intervals corresponding to the planet's orbital period. The pattern is so well understood that astronomers can extract the planet's radius, orbital inclination, and even atmospheric composition from the shape of the dip alone. The light curve of V1400 Centauri during the 2007 event looked nothing like this. There was no clean dip, there was no flat bottom, there was no smooth ingress and egress. Instead, the brightness record was a jagged, chaotic mess of peaks and valleys, rapid fluctuations, and deep plunges that varied wildly from night to night and even within a single night. On some evenings, the star shone at nearly full brightness. On others, it dropped to less than 5% of its normal output. The transitions between bright and faint states happened on timescales as short as 10 minutes, meaning that whatever was blocking the star had structure on scales comparable to the projected size of the star itself. This is where the detective work began. A solid, opaque sphere passing in front of a star produces a simple light curve, but a disk made of multiple concentric rings with varying densities produces something much more complex. As the disk drifts across the face of the star, different rings intercept the starlight at different times. A dense ring blocks nearly everything. A sparse ring lets most of the light through. A gap between rings allows full starlight to pass unobstructed. The star's brightness at any given moment depends on which specific portion of the disk happens to be covering the stellar disk at that instant. As the disk moves, the brightness changes continuously, encoding the radial structure of the entire ring system into a sequence of brightness measurements over time. Reading this code requires knowing two things. First, how fast the disk is moving across the star. Second, how large the star is. The transverse velocity of the occulting object was estimated at approximately 35 kilometers per second, derived from the total duration of the eclipse and the assumption that the disk is roughly circular. The diameter of V1400 Centauri is known from its spectral type and luminosity to be approximately 1.1 times the diameter of our Sun, or about 1.5 million kilometers. Together, these values set the spatial scale. Each minute of observation corresponds to a specific distance across the disk. 10 minutes equals roughly 21,000 kilometers of disk structure. The rapid brightness variations observed in the data therefore correspond to ring features tens of thousands of kilometers wide, well within the resolution achievable from the combination of transit velocity and stellar diameter. Kenworthy and Mamarjek used this information to build a forward model. They constructed a simulated disk with adjustable ring positions, widths, and opacities. then calculated what the resulting light curve would look like as the model disk crossed in front of a simulated star. They adjusted the ring parameters until the simulated light curve matched the observed one as closely as possible. The best fit model required 37 distinct rings, with radii ranging from approximately 30 million kilometers at the inner edge to 90 million kilometers at the outer edge. The rings varied in opacity from nearly transparent to almost completely opaque. The model reproduced the observed brightness variations with impressive fidelity, capturing the major dips, the rapid fluctuations, and the overall symmetry of the event. The symmetry was a crucial constraint. In a well-behaved transit, the ingress pattern should mirror the egress pattern because the same disk structure crosses the star in reverse order on the way out. The observed light curve exhibited this approximate symmetry, confirming that the occulting structure was a disk rather than an irregular cloud of debris. The symmetry was not perfect, however, and the slight asymmetry allowed the team to constrain the tilt of the disk relative to the transit path. The best fit inclination was approximately 13 degrees, meaning the disk was nearly but not exactly face on to the observer during the transit. This small tilt explained both the overall mirror symmetry and the minor differences between the first and second halves of the event. The model also constrained the disk's vertical structure. If the disk were very thick, puffed up like a torus rather than flat like a sheet, the transit would have lasted longer and the brightness variations would have been smoother. The sharp, rapid fluctuations observed in the data indicated a thin disk with a height-to-radius ratio of approximately 0.0015. At the outer edge of the disk, this corresponds to a vertical thickness of roughly 130,000 kilometers. Thin by the standards of the disk's diameter, but still a substantial vertical extent. The disk is not perfectly razor-flat. It has some vertical structure, which affects how it blocks starlight at different positions along its width. All of this analysis rested on data from a single event. The eclipse has never repeated. Continuous monitoring of V1400 Centauri since 2007, including observations by dedicated amateur astronomers coordinated through the American Association of Variable Star Observers, has not revealed any further dimming episodes that match the 2007 event. This is simultaneously the most important fact about J1407b and the most frustrating one. A second eclipse would confirm the ring model, refine the geometry, and immediately solve several outstanding questions about the system's orbital configuration. Without a second eclipse, the entire reconstruction rests on one 56-day window of data collected by robotic cameras that were not even designed to study this star. The absence of a repeated eclipse is itself informative. If J1407b orbits V1400 Centauri on a circular path with the transverse velocity implied by the 2007 event, its orbital period would be roughly 200 days. An object with a 200-day period should have transited the star multiple times since 2007. The fact that no additional transits have been observed means one of several things. The orbit could be highly eccentric, with a long orbital period of many years, and the companion simply has not returned to the transit position yet. Alternatively, the orbital plane could be precessing, gradually tilting so that subsequent orbits no longer carry the companion directly across the face of the star from our perspective, or the companion might not be orbiting the star at all. This last possibility is the most radical and has gained increasing attention over the years. If J1407b is not gravitationally bound to V1400 Centauri, the 2007 eclipse was not a transit in the traditional exoplanetary sense. It was a chance alignment, a coincidence in which a free-floating substellar object with a massive disk drifted between the star and Earth along our line of sight. Such events are extraordinarily unlikely for any given star, but they are not impossible, especially in a region of space populated by young stars and substellar objects like the Scorpius-Centaurus association. The evidence bearing on this question is complicated and still evolving. In 2017, a team led by Kenworthy used the Atacama Large Millimeter Array, known as ALMA, to search for J1407b directly. ALMA detects thermal radiation from dust at millimeter wavelengths, which means it can potentially image a dusty disk even when the central object is too faint to see in visible light. The observations found no source at the expected position for a bound companion near the star. However, they did detect a faint source at an angular separation of approximately 438 milliarcseconds from V1400 Centauri. At the star's distance of roughly 450 light-years, this corresponds to a projected separation of approximately 61 astronomical units, far too distant to match any plausible bound orbit for J1407b. But there was an intriguing coincidence. If J1407b were a free-floating object that had drifted away from the line of sight since the 2007 eclipse, its expected position in 2017, based on the transverse velocity inferred from the eclipse, was marginally consistent with the location of the ALMA source. The numbers were not a perfect match, but they were close enough to raise the tantalizing possibility that the ALMA source was J1407b itself, now revealed as a rogue object moving through space independently of the star. If true, the 2007 eclipse was indeed a once-in-a-lifetime coincidence, a free-floating world with a massive disk passing in front of a young star purely by chance. The scientific community treated this result with appropriate caution. A single detection at a marginally consistent position was suggestive but far from conclusive. Confirming or refuting the identification required a follow-up observation. If the ALMA source was the same object, it should have moved to a predictable new position by the time of a second observation, carried along by its own proper motion through space. In 2023, Kenworthy's team was granted additional ALMA observing time. The second observation was carried out in 2024, and the results were published in December of 2025 in Research Notes of the American Astronomical Society by Pamela Claassen, Kenworthy, Marmajek, and collaborators. The result was a non-detection. No source was found at the position predicted by the proper motion of the 2017 ALMA object. No source was found at the 2017 position itself. The field of view was empty to a sensitivity limit of 17.5 microjanskis. This means one of two things. Either the 2017 detection was a noise spike, a statistical fluctuation in the data that mimicked a real source, or the object detected in 2017 was real but had faded or changed in a way that made it undetectable by 2024. The non-detection has important implications for the physical properties of J1407b's disk, regardless of whether the object is bound or free-floating. ALMA detects thermal emission from dust grains, and the sensitivity of the observation places an upper limit on the amount of millimeter-sized dust the disk can contain. Specifically, the 2024 non-detection rules out a thick disk dominated by dust grains larger than 1 millimeter. However, it does not rule out all disk configurations. A thinner disk, or one composed primarily of sub-millimeter-sized particles, could remain below ALMA's detection threshold while still being opaque enough to block visible starlight during a transit. The disk could be real, massive, and capable of producing the observed eclipse without being bright enough at millimeter wavelengths for ALMA to detect. Kenworthy himself summarized the situation on his research page with measured optimism. The ALMA non-detection does not mean the rings are not there. Looking for the rings with ALMA was always a long shot, because the telescope would only be able to detect the most massive and geometrically thick disk configurations. The team continues to believe that the 2007 eclipse was caused by a real structure passing in front of V1400 Centauri, and they are waiting for another eclipse to confirm the light curve model and solve the orbital geometry once and for all. The nature of the central object itself remains deeply uncertain. The mass of J1407b has been estimated through several indirect methods, none of which provide a definitive answer. If the object orbits V1400 Centauri, its mass can be constrained by the orbital dynamics and the stability of its disk. A 2016 study by Stephen Reeder and Matthew Kenworthy found that if J1407b orbits the star on an eccentric path, the star's gravitational influence during close approaches would destabilize the disk unless the central object has a mass of at least 20 Jupiter masses. At that mass range, J1407b would not be a planet in the conventional sense. It would be a brown dwarf, a substellar object too massive to be classified as a planet, but not massive enough to sustain hydrogen fusion and become a true star. Brown dwarfs occupy a grey zone in astrophysical classification, typically defined as objects with masses between roughly 13 and 80 Jupiter masses. A 2018 study offered a somewhat lower mass range, finding that 5 to 20 Jupiter masses could be marginally consistent with the observations depending on assumptions about the disk's structure and evolution. The Extrasolar Planets Encyclopedia lists a mass estimate of 20 plus or minus 6 Jupiter masses, placing the object squarely in the ambiguous territory between the heaviest planets and the lightest brown dwarfs. Without a direct measurement of the object's luminosity or spectrum, which would require either resolving it in an image or observing its gravitational influence on the star's radial velocity, the mass remains uncertain. This classification ambiguity matters for how we interpret the ring system. If J1407b is a massive gas giant, the disk is a circumplanetary disk, a structure analogous to the accretion disks from which Jupiter's and Saturn's moons formed in our own solar system. If it is a brown dwarf, the disk might be better described as a circumsubstellar disk, and the forming bodies within it might be more appropriately called planets than moons. The physical processes are the same either way. Dust and gas orbit the central object, collisions and gravitational interactions concentrate material, and larger bodies gradually accrete from the disk. But the terminology and the conceptual framing differ depending on whether the central object is planet-like or star-like. The orbital stability problem adds another layer of complexity. Reader and Kenworthy's 2016 analysis showed that regardless of J1407b's mass, its disk extends to a significant fraction of, or beyond its Hill radius, the region of space within which the object's gravity dominates over that of the host star. A disk that fills or overflows the Hill sphere is vulnerable to tidal stripping by the star, especially during close orbital approaches. For a bound companion on an eccentric orbit, each periapsis passage would shear off the outer portions of the disk, gradually shrinking it over time. The proposed solution was retrograde rotation. If the disk orbits J1407b in the opposite direction to the object's orbit around the star, it gains a degree of dynamical protection against tidal disruption. Retrograde material spends less time near the star's gravitational influence during each orbital pass, reducing the rate of stripping. Reader and Kenworthy showed that a retrograde disk could survive for approximately 10,000 years before being significantly eroded, compared to only a few orbits for a prograde disk. This is a short timescale by astronomical standards, but it is long enough for the disk to persist through hundreds of orbital periods if the orbital period is measured in years or decades. A 2024 preprint by Wenshui Liu at Henan Normal University in China offered a possible mechanism for producing retrograde rotation. Liu's simulations showed that during the early chaotic phase of giant planet formation, gravitational interactions between multiple forming planets can scatter one of them into a highly eccentric orbit, while simultaneously reversing the rotational direction of its circumplanetary material. If this happened to J1407b, it would explain both the eccentric orbit and the retrograde disk in a single dynamical event. However, this work has not yet been peer-reviewed, and the scenario remains speculative. There is also the question of the disk's tilt. The light curve analysis shows that the disk is inclined by approximately 13 degrees relative to the plane of J1407b's motion across our line of sight. If the object orbits V1400 Centauri, the disk's tilt relative to the orbital plane should evolve over time due to the star's gravitational torque. The star's influence should gradually realign the disk to the orbital plane, erasing any initial tilt over timescales that depend on the disk's mass and the orbital parameters. The fact that the disk retains a measurable tilt may indicate that the system is young enough that realignment has not yet completed, or that some other process is maintaining the tilt against the star's influence. All of these uncertainties circle back to a single fundamental problem. The 2007 eclipse is the only direct evidence for the ring system. Every model, every mass estimate, every stability calculation, every interpretation depends on a 56-day stretch of brightness measurements from 2 robotic cameras that were not designed to study this star. The data are real. The eclipse happened. The ring model fits the observed light curve with high fidelity, but the lack of a second eclipse, the non-detection by ALMA, the uncertain orbital period, and the ambiguous nature of the central object all mean that the story of J1407b remains scientifically incomplete. What is confirmed is narrow but solid. A young sun-like star, approximately 450 light-years away, underwent a deep, prolonged, complex dimming event in 2007. The dimming lasted 56 days and reached a maximum depth of more than 95%. The pattern of brightness variations is consistent with a disk of at least 37 rings passing in front of the star at a transverse velocity of approximately 35 kilometers per second. The disk has a radius of approximately 0.6 astronomical units and contains at least one prominent gap suggestive of a forming satellite. The total mass of the disk is approximately 1 Earth mass. No second eclipse has been observed. The central object has not been directly detected. What is debated is almost everything else. The mass and classification of J1407b, whether it orbits the star or floats freely, whether the disk rotates, prograde, or retrograde, whether the disk can survive long-term against tidal disruption, whether the ALMA source detected in 2017 was the same object, whether the eclipse will ever be observed again. What is speculative but plausible is the broader interpretation. The disk may be a circumplanetary or circumsubstellar accretion disk in which moons or even small planets are actively forming. The gaps may be swept clean by orbiting bodies comparable in mass to Earth or Mars. The disk may represent a snapshot of a phase in planetary system evolution that is common among young giant planets and brown dwarfs, but has never been directly observed until now. The scientific community continues to watch V1400 Centauri. Amateur astronomers around the world monitor its brightness nightly through the AAVSO network, waiting for the next eclipse. If J1407b is a bound companion with a period of 10 years or more, a second eclipse could occur at any time. When it does, it will provide an immediate, powerful test of the ring model. The ingress pattern should mirror what was seen in 2007. The fine structure should match. The gap at 60 million kilometers should reappear in the same position relative to the rest of the disk. If the pattern matches, the ring model will be confirmed beyond reasonable doubt. If it does not match, the model will need revision, and the mystery will deepen. That vigil deserves a moment of attention on its own, because it is one of the strangest collaborative projects in modern astronomy. Scattered across dozens of countries, individual observers with backyard telescopes and small observatory setups photograph V1400 Centauri on every clear night. The star is faint, roughly magnitude 12, invisible to the naked eye but accessible to modest amateur equipment with CCD cameras and careful calibration. Each observer measures its brightness relative to nearby comparison stars, uploads the data to the AAVSO's online database, and moves on to the next target on their list. Most nights, the measurement is unremarkable. The star shines at its normal brightness. Nothing has changed. The observer logs the result and goes to bed. This has been happening, night after night, year after year, for well over a decade. Thousands of individual measurements accumulating into a flat, featureless line on a graph, each data point confirming that the eclipse has not returned. The patience required for this kind of work is difficult to overstate. These are not professional astronomers with guaranteed salaries and institutional backing. Many are hobbyists who spend their own money on equipment and their own evenings in the cold, contributing data to a project that may never produce a result during their lifetimes. They monitor V1400 Centauri, not because they expect to see something tonight, but because someone needs to be watching on the night it finally happens. The eclipse, if it comes, will not announce itself in advance. There will be no warning. One evening the star will simply be fainter than it should be. By a few percent at first, perhaps, as the outermost rings begin to cross the stellar disk, then deeper, then erratic, flickering, plunging, exactly as it did in 2007. The observer who catches that first anomalous measurement will trigger an alert that propagates through the astronomical community within hours. What happens next would be dramatically different from what happened in 2007. When the original eclipse occurred, nobody was watching. The data sat in an archive for 3 years before anyone noticed. This time, the community is prepared. Professional observatories around the world maintain target of opportunity protocols for exactly this kind of event. Within a day of a confirmed dimming alert, large telescopes could swing toward V1400 Centauri and begin collecting data at resolutions and wavelengths that SuperWASP never approached. Spectrographs could analyze the starlight filtering through the ring material, revealing the chemical composition of the disk particles for the first time. Is the material primarily water ice, as in Saturn's rings? Does it contain silicate dust, carbon compounds, organic molecules? The spectrum of transmitted starlight would answer these questions directly, providing compositional data that the 2007 light curve could never deliver. High-speed photometry from professional instruments could resolve brightness variations on timescales of seconds rather than minutes, revealing ring structure at scales 10 times finer than the original data permitted. The 37 rings identified in the 2015 model represent the resolution limit of the SuperWASP data. A second eclipse observed with modern high-cadence photometers could resolve hundreds of individual ringlets, mapping the disk's radial structure with precision comparable to what Cassini achieved for Saturn's rings through direct imaging. The disk would go from a coarse model with 37 bands to a detailed map with hundreds of features, each one providing constraints on the physics of particle distribution, gap formation, and satellite accretion. Simultaneously, multi-wavelength observations could probe the disk's vertical structure and particle size distribution. Infrared telescopes would detect thermal emission from the disk material itself, constraining the temperature of the particles and their distance from the central object. Radio observations could search for signatures of larger bodies within the disk, rocky cores or forming moons that emit at longer wavelengths. Polarimetry could reveal how light scatters off the ring particles, distinguishing between icy grains and rocky dust based on the polarization signature. Each wavelength would add a different layer of information, transforming the disk from a brightness profile into a three-dimensional physical model. The contrast between the 2007 dataset and what a second eclipse would yield is almost painful. The original discovery was made with data that nobody was trying to collect, from instruments that were not designed for this purpose, analyzed years after the fact. A second eclipse, observed in real time by a prepared global network of amateur and professional astronomers, would produce a dataset orders of magnitude richer. It would be the difference between glimpsing a landscape through a keyhole and walking through the front door. Until then, the rings of J1407b exist in a peculiar scientific limbo. They are the best explanation for a well-documented astronomical event. They are consistent with everything we know about circumplanetary disk physics. They were discovered by one of the most reliable detection methods in exoplanet science. And yet they have been observed exactly once, for exactly 56 days, and have left behind no trace that any current telescope can confirm independently. The largest ring system ever found is also one of the most elusive objects in the sky, hiding in the data from a single unrepeated event, waiting for the next alignment to prove itself real. There is a photograph taken by the Cassini spacecraft in 2013 that has become one of the most widely shared images in the history of space exploration. It shows Saturn from behind, backlit by the sun, with the planet's shadow falling across its own rings. The rings glow with transmitted sunlight, thin and luminous and impossibly delicate. And there, in the gap between the main rings and the faint G ring, barely visible against the blackness of space, is a tiny pale blue dot, Earth. Our entire world, every person who has ever lived, every city, every ocean, every war, every poem, reduced to a speck of light smaller than a single pixel, framed by the rings of another planet. That image works because Saturn's rings provide a sense of scale that makes Earth's smallness visceral. The rings are the frame, Earth is the subject, and the message is clear. We are small, but that message depends on Saturn's rings being large, and they are large by human standards. 270,000 kilometers across the main rings, wider than 20 Earths. A structure grand enough to humble anyone who takes the time to think about what it represents. Now imagine the same photograph taken from within the ring system of J1407b. The rings are no longer a graceful band framing a distant dot. They are everywhere. They fill the sky in every direction, stretching to the horizon and beyond, a plain of dust and ice extending 90 million kilometers from the central object. Earth would not appear as a dot in the gap between rings. Earth would be lost entirely, embedded somewhere within the disk, indistinguishable from the particles surrounding it. At the scale of J1407b's ring system, Earth is not small. Earth is irrelevant. It is a rounding error in a structure that occupies more space than our planet's entire orbit around the Sun. This is not a comfortable comparison, and it is not meant to be. The ring system of J1407b forces a confrontation with the range of structures that the universe is capable of building around individual worlds. Saturn's rings taught us that planets can wear halos of debris. J1407b's disk teaches us that those halos can grow large enough to swallow inner solar systems. And the difference between these two lessons is not one of degree, it is one of kind. Saturn's rings are jewelry. This disk is architecture. The most scientifically significant aspect of the J1407b system is not its size, but what its size implies about a process we have never directly observed: moon formation. Every large moon in our solar system is believed to have formed from a circumplanetary disk, a flattened structure of gas and dust orbiting a giant planet during the early history of the solar system. Jupiter's 4 Galilean moons, Io, Europa, Ganymede, and Callisto, are thought to have accreted from such a disk approximately 4.5 billion years ago. Saturn's largest moon, Titan, likely formed through a similar mechanism. The ice giants Uranus and Neptune may have had their own circumplanetary disks from which their smaller, irregular moon systems partially derive. But these primordial disks vanished billions of years ago. They were consumed by the very moons they created, drained of material, as gravitational accretion swept up the dust and gas and compacted it into spherical worlds. By the time the solar system reached its current mature state, no trace of these formation disks remained. We see the products of the process, the moons themselves, but the factory that built them closed down long before any telescope existed to observe it. J1407b, if the circumplanetary disk interpretation is correct, is that factory still operating? It is a snapshot of the moon formation process frozen at an early stage, captured by a chance alignment that allowed us to read its structure in the flickering light of a distant star. The 37 rings are not static debris bands like Saturn's. They are lanes of raw material feeding the growth of new worlds. The gaps are not empty voids maintained by tidal resonances with distant moons. They are construction zones where forming satellites have gathered enough mass to clear their orbital neighborhoods, sweeping up particles and growing larger with each orbit. The prominent gap at approximately 60 million kilometers from the central object is the strongest evidence for this interpretation. A gap 4 million kilometers wide, carved into a disk that is otherwise dense with material, requires a body massive enough to gravitationally dominate its local environment. The estimated mass for such a body is less than 80% of Earth's mass, a world potentially comparable in size to Mars or Venus. If this estimate is correct, The J1407b system contains a forming moon that is already larger than any moon in our solar system. Ganymede, Jupiter's largest moon and the largest moon in our solar system, has a mass of approximately 2.5% of Earth's mass. The moon inferred from J1407b's gap could be more than 30 times more massive. It would not be a moon in the way we typically imagine moons. It would be a world in its own right, comparable in mass to a terrestrial planet, orbiting not a star but a giant planet or brown dwarf. A second, narrower gap hints at a second forming body, though the evidence is less definitive. If multiple moons are indeed forming within this disk, the system may be assembling an entire satellite family simultaneously, each body carving its own lane through the dust and growing at the expense of its surroundings. This is precisely what theoretical models of circumplanetary disk evolution predict. Moons do not form one at a time. They form together, competing for material, interacting gravitationally, migrating inward or outward through the disk as they grow. The Galilean moons of Jupiter show signs of this shared formation history in their orbital resonances. Io, Europa, and Ganymede are locked in a precise gravitational relationship in which Io completes exactly 4 orbits for every 2 of Europa and every 1 of Ganymede. This resonance is thought to have been established during the formation process itself, as the moons migrated through the primordial disk and locked into gravitationally stable configurations. If a similar process is unfolding within the J1407b disk, the moons being built today may eventually settle into their own resonant configuration, a system of worlds orbiting in lockstep around a central body that is itself orbiting a star or drifting freely through interstellar space. Either way, the outcome would be a miniature planetary system, a collection of worlds built not from a stellar nebula but from a circumplanetary disk, governed by the same physics that built the satellite systems of Jupiter and Saturn, but operating at a dramatically larger scale. The total mass of the disk supports this interpretation. At approximately 100 lunar masses, or roughly 1.25 Earth masses, the J1407b disk contains far more raw material than Saturn's rings, which have a total mass less than half that of the small moon Mimas. Saturn's rings are insufficient to build anything substantial. They contain barely enough material to assemble a body a few hundred kilometers across. The J1407b disk contains enough material to build several large moons, potentially rivaling or exceeding the Galilean satellites in mass. The budget is there. The physics permits it. The gaps suggest it is already happening. This matters beyond the specifics of one system because it connects to a broader question that planetary science has struggled to answer. How common are large moons around giant exoplanets? Despite the discovery of thousands of exoplanets over the past 3 decades, not a single exomoon has been definitively confirmed. Several candidates have been proposed, most notably Kepler 1625bi, a Neptune-sized moon candidate orbiting a Jupiter-sized planet approximately 8,000 light-years away. But the detection remains disputed, with some analyses supporting the moon hypothesis and others attributing the signal to stellar variability or systematic errors in the data. As of the present, the confirmed exomoon count stands at 0. This absence is puzzling because moons should be common. In our solar system, every giant planet has multiple moons. Jupiter has 95 known moons. Saturn has over 140. Even the ice giants have dozens. If giant planets routinely form with circumplanetary disks, and if those disks routinely produce moons, then the exoplanet population should include billions of exomoons scattered across the galaxy. We do not see them because they are extraordinarily difficult to detect. Moons are small. Their transit signals are tiny, buried in the noise of stellar variability and instrumental systematics. Their gravitational influence on their host planets is subtle, producing timing variations that are at the edge of current measurement capabilities. The tools exist in principle. The sensitivity does not yet exist in practice. J1407b does not solve this problem directly. It does not confirm the existence of any specific exomoon. but it provides something almost as valuable. It provides evidence that the formation process that should produce exomoons actually occurs in nature at scales large enough to generate massive satellite systems. If circumplanetary disks this substantial exist around young substellar objects, then the theoretical prediction that giant planets routinely form moons from such disks is not just a model, it is an observed phenomenon. The moons may not be visible yet, but the factories that build them are. The age of the host star reinforces this point. V1400 Centauri is approximately 16 million years old. In the timeline of planetary system evolution, 16 million years is early. The Sun is 4.5 billion years old. 16 million years is less than 0.4% of the Sun's current age. At this stage, planets have formed or are still forming. Disks of debris and gas still surround young objects, and the processes that will shape the final architecture of the system are actively underway. Observing a massive circumplanetary disk at this age is like visiting a construction site in the first week of a project that will take years to complete. The foundations are being laid, the framework is going up. The final structure is not yet visible, but the plans are encoded in the arrangement of materials. Theoretical models predict that circumplanetary disks around young giant planets should dissipate over timescales of a few million to a few tens of millions of years, as material is consumed by forming moons, accreted onto the central planet, or dispersed by radiation and stellar winds. At 16 million years, the J1407b disk is either in the late stages of this dissipation or is being replenished by material from the surrounding environment. If the disk is shrinking, it may represent one of the last opportunities to observe this phase of satellite formation before the disk disappears entirely and only the finished moons remain. If it is being replenished, the disk could persist for longer, extending the window for observation but also complicating models of disk evolution. This raises a question that has not yet been addressed directly. What will this system look like when the construction is finished? If the disk dissipates over the next several million years, consumed by the moons it is building, what remains? The answer depends on how efficiently the disk converts its material into satellites. If the process is highly efficient, most of the disk's roughly 1 Earth mass of material will end up concentrated in a handful of large moons. The gaps currently visible in the light curve will widen and merge as the forming bodies sweep up everything in their orbital zones. The remaining dust between the moons will thin to insignificance, dispersed by radiation pressure or accreted onto the moons themselves. What was once a disk spanning 180 million kilometers will become a set of discrete worlds orbiting the central object at various distances, each one a finished product of the gravitational machinery that is currently running at full capacity. If the primary gap really does contain a body approaching 80% of Earth's mass, the finished satellite system could include worlds with solid surfaces, atmospheres, and potentially subsurface oceans heated by tidal forces from the massive central object. These would not be the small, inert moons that populate the outer regions of our solar system's giant planets. They would be worlds with geological activity, with weather, with the raw conditions that planetary science increasingly recognizes as relevant to habitability. A brown dwarf orbited by a terrestrial mass moon heated by tidal friction is, in some theoretical frameworks, a plausible environment for liquid water. Not likely. Not confirmed, but not ruled out. The disk around J1407b may be building worlds that matter for astrobiology, not just for orbital mechanics. Now, turn that timeline backward rather than forward. If J1407b's disk is 16 million years old and still assembling moons, what did our own solar system look like at the same age? When the Sun was 16 million years old, Jupiter and Saturn had likely already formed their cores and accreted their massive gas envelopes. Their own circumplanetary disks were either still active or had recently dissipated, depending on how quickly their moons assembled. The Galilean moons may have been in the final stages of formation, still embedded in the remnants of Jupiter's disk, still accumulating their last increments of mass. Titan may have been coalescing inside Saturn's disk, gathering the nitrogen-rich material that would eventually form its thick atmosphere. The solar system, at 16 million years old, was a construction site too. We simply arrived 4.5 billion years too late to see it. J1407b lets us see it. Not our own system, but one that may be undergoing the same fundamental processes at the same fundamental stage. The disk is a window into the past, not through time travel but through the statistical fact that the universe contains young systems at every stage of development, and occasionally one of them crosses our line of sight at the right moment to be studied. Somewhere in the disk of J1407b, the same physics that built Io and Europa and Ganymede and Titan is operating right now, assembling new worlds from the same raw ingredients, following the same gravitational rules, producing outcomes we can only begin to predict. The possibility that J1407b is a free-floating object rather than a bound companion to V1400 Centauri adds an unexpected and deeply strange dimension to this story. If the central object is a rogue planet or brown dwarf drifting through space without a host star, the disk takes on a different character entirely. It is not being sculpted by the gravitational influence of a nearby star. It is not being heated by stellar radiation. It is not orbiting anything. It is evolving in isolation, governed only by the gravity of the central object and the internal dynamics of the disk material. Picture what that means. A world perhaps 20 times the mass of Jupiter, dark, warm only from its own internal heat, glowing faintly in the infrared at a temperature of perhaps a few hundred degrees. No star illuminates it. No stellar wind erodes its disk. It drifts through the interstellar medium of the Scorpius-Centaurus association, surrounded by a flat disk of dust and ice that extends 90 million kilometers in every direction from its equator. The disk is not lit by any external source. It is visible only by its own faint thermal emission, and even that is so dim that the most powerful radio telescope on Earth could not confirm it when it tried. Inside this disk, moons are forming. Particles collide, dust grains stick together. Larger bodies grow through accretion, gaps open as forming satellites clear their orbital lanes. All of this happens in darkness. There is no sunrise on these forming worlds. There is no day. The only light is the dull infrared glow of the central brown dwarf and the faint thermal radiation of the disk particles themselves. A satellite system is being assembled in conditions that look nothing like the sunlit environment where Earth's moon or Jupiter's moons formed. It is being built in the cold dark between stars by an object that may have been ejected from its birth system billions of years ago or may have formed in isolation from a collapsing fragment of a molecular cloud. This possibility sounds exotic, but it may not be rare. Surveys of young star-forming regions have detected significant populations of free-floating planetary mass objects, some of which appear to have been ejected from their birth systems through gravitational interactions with other planets. If some of these ejected objects carry remnants of their circumplanetary disks with them, the galaxy could host a population of rogue worlds surrounded by rings or disks that we have never detected, because there is no convenient background star to illuminate them. J1407b may be one member of a much larger class of objects that we are only beginning to recognize. Dark worlds with dark disks, building dark moons, drifting through the galaxy unseen. The only reason we know about this one is that it happened to pass between us and a star, a geometric coincidence that may occur once and never repeat. This brings the story to a question that reaches beyond any single system or any single discovery. What does it mean that the universe builds structures this large around individual worlds? Saturn's rings are the most beautiful feature in our solar system. They are graceful, photogenic, and instantly recognizable. Every child who has ever drawn a planet has drawn Saturn, the yellow circle with the line through it. The rings are the symbol, the icon, the defining image of what a planet can look like. And for centuries, they were the upper limit of what we thought planetary ring systems could be. Saturn represented the extreme case, the most the universe could produce in terms of rings around a world. J1407b demolishes that assumption completely. The universe does not build ring systems that max out at Saturn's scale. It builds ring systems that span the width of planetary orbits, contain the mass of entire terrestrial worlds, host forming moons larger than anything in our solar system, and stretch across regions of space so vast that light needs 10 minutes to cross them. Saturn's rings are not the ceiling, they are the floor. They are the quiet, diminished remnant of a process that once operated at scales we are only now beginning to detect. And this is the point that changes how we should think about the cosmos. Not that J1407b is large in some abstract numerical sense. Not that 180 million kilometers is bigger than 270,000 kilometers, but that the range of structures the universe builds around worlds is far wider than our local solar system suggests. We grew up in a planetary system where the largest ring system is delicate, low mass, and temporary. We assumed that was normal. We assumed that was representative. We assumed Saturn showed us the general case. It did not. Saturn showed us one specific case, one data point, one example drawn from a distribution whose upper end we had never sampled. J1407b shows us what the upper end looks like, and the upper end is terrifying. Not terrifying in the way of a threat. There is no danger. This disk is 450 light-years away and has no influence on anything in our solar system. Terrifying in the way that genuine confrontation with scale is always terrifying. The realization that the universe operates on ranges that make our most impressive local features look modest. The understanding that what we considered extraordinary is actually ordinary, and that what we considered the limit was never a limit at all. Consider the progression. Before Galileo, nobody knew ring systems existed. After Galileo, Saturn's rings seemed unique and mysterious. After Voyager, we learned that all 4 giant planets have rings, but Saturn's was still the grandest. After J1407b, we know that ring systems can be hundreds of times larger than Saturn's, that they can contain planet masses of material, and that they can serve as factories for building entire satellite systems around young worlds. Each step in this progression expanded the range of what we thought the universe was capable of. Each step pushed the boundary outward, and there is no reason to think J1407b represents the final boundary. The detection method that found this system, transit photometry, is sensitive only to ring systems that happen to cross our line of sight to a background star. The geometric probability of this alignment is small. For every ring system we detect through transit, there may be hundreds or thousands oriented at angles that prevent us from seeing them. J1407b was discovered because a young substellar object with a massive disk happened to pass in front of a young star as seen from Earth. If the alignment had been off by a fraction of a degree, we would never have known the disk existed. The question of how many similar systems exist in the galaxy but remain undetected because of unfavorable geometry is genuinely unsettling. The answer could be enormous. Future observatories may begin to constrain this number. The Vera Rubin Observatory, expected to begin full operations within the next few years, will conduct a decade-long survey of the entire visible sky, monitoring billions of stars for brightness variations. Its unprecedented combination of depth, coverage, and cadence makes it sensitive to the kind of prolonged, complex dimming events that revealed J1407b. If similar systems exist around other young stars, the Rubin Observatory has a realistic chance of finding them. Each new detection would expand our understanding of how common massive circumplanetary disks are, how they vary in size and structure, and how they relate to the properties of their central objects. The James Webb Space Telescope offers a different avenue. While Webb cannot monitor millions of stars simultaneously the way survey telescopes do, it can characterize individual systems in extraordinary detail. If a second eclipse of V1400 Centauri occurs, Webb could observe it in infrared wavelengths, probing the composition and temperature structure of the ring material in ways that ground-based visible light photometry cannot. Webb could detect thermal emission from large forming moons within the disk, potentially confirming the ex-moon candidates inferred from the gap structure. It could constrain the mass and temperature of the central object through spectroscopy, resolving the planet versus brown dwarf debate that has lingered since the initial discovery. But the deepest implication of J1407b is not about future telescopes or future discoveries. It is about the limits of extrapolation from a single example. For decades, our understanding of ring systems, moon formation, and circumplanetary disk physics was built almost entirely on observations from our own solar system. Saturn was the prototype. The Galilean moons were the model products. Everything else was theoretical, inferred, simulated. J1407b is one of the first pieces of direct evidence from outside our solar system, and it immediately showed that our prototype was not representative. The first circumplanetary disk we detected beyond our neighbourhood was not a modest structure comparable to what we expected. It was a monster, 200 times larger than anything in our local experience, containing enough mass to build a satellite system that would dwarf Jupiter's. This pattern recurs throughout the history of astronomy. Every time we develop the ability to observe a new class of object beyond our solar system, we find that the local examples we relied on were not typical. The first exoplanets discovered were hot Jupiters, gas giants orbiting their stars in days rather than years, something that did not exist in our solar system at all. The first exoplanetary atmospheres characterized showed compositions and temperature profiles unlike anything predicted from solar system models. And now, the first detected circumplanetary disk is hundreds of times larger than the ring system we treated as the benchmark. The universe is not constrained by our examples. It builds what physics allows across the full range of conditions, timescales, and scales that nature makes available. Our solar system samples one point in that range. J1407b samples another. The gap between them is vast, and the territory between remains almost entirely unexplored. Stand outside on a clear night and find Saturn in the sky. If it is visible, it will appear as a steady yellowish point of light, unremarkable among the brighter stars. Even through a telescope, its rings are subtle, requiring magnification and patience to resolve. Those rings, the most famous and beloved structure in our planetary system, contain less mass than a single mid-sized icy moon. They are 270,000 kilometers wide and 10 meters thick. They are beautiful, they are temporary, and they are, by the standards set by J1407b, vanishingly small. 450 light-years away, an object we have never directly seen carries a disk of dust and ice that stretches across 180 million kilometers, 37 rings. Gaps where worlds are forming. Enough material to build a system of moons that could rival anything in our solar system. We detected it through a 56-day flicker in a star's brightness, recorded by cameras that were not watching for it, noticed by a graduate student 3 years after the fact. It has never been seen again. It may never be seen again from this angle, and yet the evidence that it exists is written into the light curve with a precision that permits no comfortable alternative explanation. The terrifying part is not that this ring system is large. The terrifying part is what its existence tells us about the universe we live in. It tells us that the cosmos builds structures around individual worlds that are so vast they make Saturn's rings look like a trace of frost on a window pane. It tells us that the processes shaping planetary systems operate across a range of scales we had never sampled until a chance alignment gave us a 56-day glimpse. And it tells us that for every system we happen to detect, there may be countless others hidden in the dark, tilted away from our line of sight, assembling worlds we will never see around objects we will never know exist. Saturn is not the upper limit. Saturn is not even close. And the universe, as always, is larger, stranger, and more capable than we assumed.